Hi everyone, this is week 4, lecture 2. This lecture is on the classical assumptions. That's what they're called. It's a set of assumptions about the components that make up the linear regression model. So as I said last time, we're doing the simple regression model again, but we're adding a layer of important statistical detail, this time governed by the classical assumptions. So in the last lecture, we talked about probability distributions. Some of the concepts will be a review, I hope, but we need to be able to refer to things like the standard normal distribution or the normal distribution and refer to that, and you all know what I'm talking about, and you can picture it in your mind. You know what that means. This week, we're building up the statistical foundations of regression modeling. And next week, we're going to learn the properties of the estimators that come out of a regression model, and they're going to be based on these assumptions that we learned today. In fact, today's lecture is kind of the agenda for the rest of the course. Now, the thing is, today's lecture won't really take too long. You'll find it's a bit of a short lecture, even though it's somewhat dense on material, and the section of the textbook isn't very long either. Next week, there's only one lecture, because next week is the mid-semester break. But the lecture for next week is a bit on the long side. So if you have extra time this week, you might want to get an early start on the stuff that we do next week so that you get to enjoy some of your break time and you're not having to work all weekend. Hope you're keeping up with the assignments. Hope you're keeping up with the R programming material, the lab material. If you have any problems, as always, just let us know. And in the meantime, grab your pens, open your textbook. You might want to follow along. I'm going to follow along very closely with what's in the textbook. And here we go. There are two ways to write down the classical assumptions, so we'll look at both of them. So we are looking at what are called the classical assumptions, and the way I want you to think about it is like this. So we have the simplest possible regression model. So we just have the dependent variable, we have a single independent variable, we don't have a constant term, and we have the error term. You can leave a constant term out of the regression only if the independent variable and the dependent variable both have a mean of 0. And so that's an assumption we're making here. That's what lets us use the simple regression model. Okay, so this is a random variable. The error term is a random variable. And we assume that the independent variable is non-random. And you add a random and a non-random variable together, well, that gives you a random variable. And so this error term here, this is where the randomness enters the model. And in the textbook, let me just show you over here. On page 64, Professor Koop lists the classical assumptions, but he lists them in terms of properties of the y, the dependent variable. And then over a page on page 66, he relists them as properties of the error term. Now, typically in these textbooks, we list them as properties of the error term. By stating the properties of the error term, that implies properties of the dependent variable, but it's kind of easier, I think of them as properties of the error term because that's where the randomness enters the model. So that's what I'm going to focus on. I'm going to emphasize the list on page 66 rather than the list on page 64, but I will put both versions up for us. One of the odd things about my document camera that I'm using is that I have a lapel mic on so that it records better volume, but the document camera has a default setting that it goes to its internal microphone, and I have to remember every time I start recording to change that over. It won't let me set the default to the lapel mic. So some segments of these videos, if it sounds like the audio goes a bit quieter or is lower quality, it's usually because I forgot to change the microphone over to the lapel mic. But I will try to remember to do that when I'm recording so that the audio is better quality, especially since I tend to mumble and talk to myself and things like that, and it'll make it a little easier for you guys to follow what I'm thinking. All right, so the first classical assumption. The first classical assumption about the error term is that the expectation of the error terms is 0, or that the error terms have a mean of 0. And if that's true, then that implies that the expected value of y lies right on the regression line. This makes sense. This essentially means that we are assuming that we're not making a systematic error in the regression model. You can think of it a couple of different ways. One is we're assuming we're not building in a predictable systematic error, that our predicted values will always be above or below the regression line. We're assuming that we're not doing that. Another way of thinking about this is we're assuming that the regression line goes through the middle of the data set. So if we drew the scatter plot like so, it makes sense to think that the regression line is going to go through the middle of the data set. It wouldn't make a whole lot of sense to say the regression line could be over here where it's completely underneath all the data, because that would mean that every error term is positive, so the expected value of the error terms itself is positive. Well, we wouldn't fit a regression line outside of the data like that. That wouldn't make any sense. So regression line goes through the middle of the data. We don't have any systematic errors, and so that means the expected value of the error term is 0. And because the expected value of the error term is 0, that means the expected value of y is a point on the regression line. One of the terms, I think it appears in the textbook, but if not in this textbook, the term is conditional mean function. A regression line is a conditional mean function. So what that means is that the mean of yi given xi equals yi hat. So conditional means we're given a certain value of x, and then the expected value of y given that value of x is yi hat, which equals xi times beta hat. Okay, so in our house price example, the mean value of a house given that it has 3 bedrooms is, and then whatever the predicted value of the regression model is, but that's not going to be the exact value of the house. That's going to be the expected or mean value for a house of that size. That's what we mean. A conditional mean function is the mean given the observation on the explanatory variable. And that interpretation makes sense only if the expected value of the error terms equals 0. Okay, on to the second classical assumption. The page 66 version is that the variance of the error term, which equals the expected value of the square of the error term, is a constant. And this implies that the variance of the dependent variable is also a constant. Now this one, why did I write that? Well, you'll remember there are two ways of writing the variance. The variance is the expected value of epsilon minus its expectation, and then we square that. Well, its expectation is 0, so that just disappears and we're left with the expected value of epsilon squared. So the variance is constant over the sample. And that means that our data, they're dispersed around the regression line, but the dispersion doesn't change over the course of the sample. Now there's a term for this. So randomness, the Greek word for randomness is skedasticity. So the error term is the skedastic term in the regression. And so since we're saying that it's the same skedasticity across the sample, this is a homoskedastic error term. So we write that by saying it's a number, which we call sigma squared, and there's no subscript on there. And because there's no subscript, that means it's the same across everywhere in the sample. So the variance of the error term is a constant. The constant happens to be called sigma squared, and that means we have a homoskedastic error term. Why is this important? Well, stay tuned. We're going to understand why all these assumptions are important, but in the case of the homoskedasticity assumption, if this variance changes over the course of the sample, then that has implications for how we should estimate our slope coefficient. So that's the second one. The third is that the covariance of any two error terms in the sample, epsilon I, epsilon j, equals 0 for I not equal to j. And that implies the covariance for any two values of the dependent variable equals 0 for I not equal to j. Okay, so this is a little bit more obscure. All of these you're going to see as we go along why they're important, why they matter. It'll make sense, but it'll take us more or less the rest of the course to figure it out. But let's suppose that this wasn't true. Let's suppose that the covariance for adjacent error terms was positive. So if covariance of epsilon I and epsilon j is greater than 0 for j equals I plus 1. All right, so observation j is the next one in the sample after observation I. So here we are at, we'll say this is x 43. So it's the 43rd observation in our data set, and this is x 44. So it's the 44th observation in the data set. And we are above the regression line. All right, so this means that epsilon 43 is greater than 0 because we're above the regression line. Well, if these have a positive covariance, that means we now have a bit of information about the next error term along here. Since these are positively correlated, or they have positive covariance, then that means this error term is also likely to be greater than 0. So it's kind of like the assumption that they all have to have an expected value of 0. If this covariance is positive, then that means we can predict at least part of this error term as we move forward in the sample. So that would mean might be smaller, might be a little larger, but it'll mean that there's a portion of this error term which we could potentially figure out and estimate. And that means our regression model isn't complete. So if our regression model is complete, what it would mean is when we know the value of the error term at observation 43 in the sample, it doesn't give us any information about what the error term is at observation 44. If that weren't the case, then that means that we could build a better regression model that would get more information out of the sample. So this assumption, there's a term for it. It means no autocorrelation. Okay, autocorrelation means, well, auto is I guess it's the Latin prefix for self. So no autocorrelation means the error terms aren't correlated with themselves. So this error term is not correlated with any of the previous error terms or subsequent error terms. Or alternatively, the epsilons are independent of each other. And by implication, it means that the dependent variables are independent of each other. So the way to think about this is this assumption means essentially that we are getting all the information out of the data that we can. We're not building a regression model that leaves some of the information in the data set unexploited or unused. And if the error terms are autocorrelated, and we don't take that into account when we're building our regression model, then it means we're not making the best use of the information in the data set. So, and we will, again, look at what happens if there is autocorrelation. First of all, how you detect it, and then how you would modify the regression model to make use of that information. All right, number 4, epsilon is normally distributed. Okay, so that means epsilon follows a normal distribution, and based on our assumptions, it has a mean of 0 and a variance of sigma squared. And the corresponding term for y is normally distributed with a mean of x beta and a variance of sigma squared. I'm just going to check in the textbook. Let's see how. Yeah, so you can see down here the assumption y is normally distributed, and just below that he writes out that it's in that form there. This assumption turns out it's not as essential as the other ones. There are lots of probability distributions. The normal distribution has a bunch of interesting advantages to it, which we'll get to talking about, including the fact that if the error terms aren't normally distributed, if our sample is large enough, we can still use the normal as a good approximation to it. So there's a branch of statistical theory called asymptotic theory. Asymptotic meaning when you have very large numbers in your sample, what do the sample properties converge on? And it turns out for a lot of stochastic or skedastic processes, they converge to looking like normal if, regardless of how what the underlying distribution is, if you transform them in the right way. Don't worry about all that for now. That we'll get to it. The important thing here is we're going to assume that it follows that bell-shaped distribution with the tail sizes that we have tables for, and so we can make probability statements based on the assumption that it's normally distributed. The fifth assumption is that X is non-random. How's that one written? Yeah, it's written the same on page 64 and 66. It's the same either way. Professor Koop uses the term fixed, which technically is true, so we're assuming that X is a non-random variable, so it's not following a distribution. So we can observe the exact value of X. But it's maybe a bit more intuitive to think of it as a non-random variable. So randomness doesn't enter the model through the X term. And so this one is another example of an assumption that we're going to look at. Well, what happens if this isn't true? What if there is randomness in the model through the X term? And then that's a bit of a complicated thing to try to deal with. Okay, so those are the classical assumptions. Now, there's a technical way of writing this. We could say that the covariance of X and epsilon equals 0. This is actually a slightly less restrictive way of expressing the assumption. So if X is non-random, then this will be true, and this is the important thing about the assumption, though, which is that the error terms and the X terms have 0 covariance. That is not the same as the homoscedasticity assumption, which concerns the variance of the error term being uncorrelated with the X's. In this case, it's the size of the error terms is also uncorrelated with the X's. Okay, so what do we get for all of these? So if all of these are true, then it's going to mean, so if all these are true, then we can use statistical tables to construct hypothesis tests and confidence intervals for beta hat. All right, so the reason we construct these statistical models is usually because we want to estimate beta hat, the size of the slope coefficient, and then say something about how big its confidence interval is, and perform hypothesis tests about it. We'll go through the assumptions one by one, and for each one we'll say, well, what if it's not true? If it's not true, and we apply the formulas that we're learning, then we'll get the wrong answers. We might get biased estimates of beta hat, or we might get biased estimates of the variance of beta hat, and then we have to figure out how to fix that. And that is really what the rest of the course is about. So I'm going to leave it at that. Make sure you've finished up to section 3.3 in the textbooks, textbook, and next week we start on the properties of the ordinary least squares estimator, and they follow from these assumptions. And as I mentioned at the beginning, since this was a short lecture, why don't you have a look at the first 20 minutes of the next lecture, and that will save you a bit of work during your break week next week. And I'll see you next time.